Welcome to the lecture series on the subject Applied Thermodynamics, Module 3, Vapor Power Cycles. This is lecture number 4. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So, in this lecture, we'll start with the discussion on the ideal reheat Rankine cycle. The TS diagram of the ideal reheat Rankine cycle and the schematic of the power plant operating on this cycle are shown in figure. So this is the schematic of the power plant operating on the ideal reheat Rankine cycle, and this is the TS diagram. The ideal reheat Rankine cycle differs from the simple ideal Rankine cycle in that the expansion process takes place in two stages. That means here expansion takes place in two turbines rather than one turbine. Now just to recall the TS diagram of the Rankine cycle, you know that 1 is the entry point to the pump, and 1 to 2 is the pump work, 2 to 3 is the heat addition in the boiler. Now usually from 3 the expansion takes place in single turbine, but in case of ideal reheat Rankine cycle you can see 3 to 4 is the expansion in the HP turbine. You see HP means high pressure turbine. Then it is the steam from the high pressure turbine. Okay, the outlet is shown here. It should not be on the straight line. We should give it from somewhere here, because entry point and exit point should not be on the same line. So exit point should be here. So please do correct that mistake. So then the exit of the high pressure turbine is fed to a reheater, that is a coil which is passing through the boiler, because the boiler, the temperature is very high, the products of combustion gases are passing. So when this steam after expansion in the HP turbine passes through this reheater, so you can see once again its temperature increases. Now if it is a perfect reheating, then T3 will be equal to T5, or it depends sometimes, so temperature may be less than T3 also. So this is 4 to 5, so this is called as reheating. Right? So reheating takes place at constant pressure. So P4 is equal to P5 is equal to reheat pressure. Now you see it undergoes expansion in the second stage turbine to 0.6. You can see this is the LP turbine. You see, this is the boiler pressure, this is the reheat pressure, and this is the pressure after the second stage. So that is why it is called as low pressure turbine. So after expansion in the second stage turbine, the pressure is very low. So then once again it is passed through the condenser. 6 to 1 is the condensation process. This is the explanation. In the first stage, that is HP turbine, steam is expanded isentripically to an intermediate pressure and sent back to the boiler, where it is reheated at constant pressure, usually to the inlet temperature of the first turbine. That is what I told you, T3 should be equal to T5. Generally T3 will be equal to T5. Steam then expands isentripically in the second stage to the condenser pressure. Thus the total heat input, the heat rejected, the total turbine work output, and the total pump work for a reheat cycle become. Now let us write the expression for the total heat input. So here Q in is Q primary plus Q reheat. So Q primary means, as all of you know, 2 to 5 is the heating, that is the boiler, wherein the water gets converted into steam. So here the heat addition is called as Q primary or primary heat addition. Then 4 to 5, once again it is the same steam is heated in the reheater inside the boiler. That means there are two heat-ins, that is Q primary as well as Q reheat. So H3 minus H2 plus H5 minus H4. And Q out, that is the heat rejection in the condenser process, is from 6 to 1, that is in this condenser. So that is H6 minus H1, or here H1 is nothing but HF1 at the condenser pressure. So you can write it as H6 minus HF1. Now W turbine. So there are two turbines, as you know. So just recall the TS diagram. So turbine 1 plus turbine 2, 3 to 4 and 5 to 6. So first turbine, HP turbine, the work output is H3 minus H4. LP turbine, the work output is H5 minus H6. Also the pump input is nothing but H2 minus H1 or HF2 minus HF1, which is also equal to V1 into P2 minus P1. So that's all of you know. The pump work is nothing but H2 minus H1, or in terms of pressure and specific volume, V1 into P2 minus P1. So net work done per kg of steam, W net, is nothing but W turbine minus W pump. So these two terms are the W turbo output, that is HP turbine and LP turbine, and this is nothing but the compressor, or sorry, pump work input. Now the thermal efficiency is nothing but net work done by heat supplied. So this is the expression for the net work done, and in the previous slide we wrote the expression for the heat supplied as H3 minus H2 plus H5 minus H4. The incorporation of single reheat in a modern power plant improves the cycle efficiency by 4 to 5% by increasing the average temperature at which heat is transferred to the steam. So a reheat Rankine cycle will improve the efficiency of the simple Rankine cycle by 4 to 5%. So incorporation of reheat improves the efficiency of the Rankine cycle. Okay. Now coming to the ideal regenerative Rankine cycle, reheating has the limited ability to improve the thermodynamic efficiency of Rankine cycle, but is quite useful in the reduction of the moisture in the turbine. So after reheat, you could have seen, you might have observed there the point 6, right? So it is more of towards right side in the two-phase region. Means quality of the steam is high at the end of the LP turbine, or at the exit of the LP turbine. So though the reheating has a limited ability to improve the thermodynamic efficiency of the Rankine cycle, but it is very useful in reducing the moisture in the turbine. However, it is observed that the largest single loss of energy in a power plant occurs in the condenser. You see H6 minus H1 if it is a reheat cycle, otherwise it is different terms. Okay, so general condenser, in the condenser, so there will be largest loss of energy, so wherein the heat is rejected into the coolant. So hence reducing this heat rejected is drastically improves the efficiency. Now you have to think of the way by which you can reduce the heat loss through the condenser. In both ideal and reheat Rankine cycle, the condensate is returned to the boiler at the lowest temperature of the cycle. Though the exit temperature from the turbine is high, but it is cooled back to its lowest temperature of the cycle before it is fed to the boiler. The fluid is heated. So now whatever the fluid which is entering the boiler is heated to the saturation by direct mixing in the steam drum of the boiler. So this is what is happening inside the boiler. So the fluid which is entering in at the lowest temperature of the cycle is heated to the saturation temperature by direct mixing in the steam drum of the boiler, by furnace radiation in both the tubes, or by gas convection by heating by the flue gases in the economizer. So this is how the temperature of the water, which is at a very lowest temperature when it enters to the boiler, is increased to the saturation level, either by mixing with the steam, or by passing with the help of furnace radiation, by passing the water in the tubes, or by gas convection heating by the flue gases in the economizer. Now all these methods involve large temperature differences and are inherently irreversible. So whenever there is a large temperature difference, the process becomes irreversible. So instead of resorting to such a procedure, a method of feed water heating is considered. So now to avoid all these difficulties, so you have to choose a method called as feed water heating. In the simple Rankine cycle, the average temperature of heat addition is quite low. So that is in the simple Rankine cycle. If the amount of heat required for this purpose is supplied internally, the cycle thermal efficiency would approach to that of the Carnot cycle. If the amount of heat required for this purpose is supplied internally, the cycle thermal efficiency would approach to that of the Carnot cycle. So whatever the heating of water from low temperature to high temperature, if it can be done internally, then your cycle efficiency will increase. This could be done in a regenerative cycle in which feed water is preheated by expanding steam. This is where you have to recover the heat of the exhaust steam from the turbine by incorporating a regenerative cycle wherein the feed water in the sense the water which has to be supplied to the boiler is preheated, means heated to a higher temperature before supply to the boiler. Okay, the thermal efficiency of the Rankine cycle increases as a result of regeneration. This is because regeneration raises the average temperature at which heat is transferred to the steam in the boiler. So once the moment the temperature at which water enters the boiler increases, right, automatically the average temperature of heat addition also increases. If the temperature at which water enters the boiler is very low, so then automatically average temperature also becomes less. A practical regeneration process in steam power plant is accomplished by extracting or bleeding steam from the turbine at various points. So how it can be accomplished in reality? So that is by extracting or bleeding of steam from the turbine at various points, and then it is used to preheat the feed water. This steam which could have produced more work by expanding further. Now you see there is a loss. So whatever the steam which is extracted or bled from the turbine, it would have expanded further and it would have converted some heat into work. But here you are not allowing it to do that. So this steam would have produced more work by expanding further in the turbine, but it is used to reheat or heat the feed water instead. The device where the feed water is heated by regeneration is called regenerator or a feed water heater. So this is very important. So you should remember the device where the feed water is heated by regeneration is called as regenerator or feed water heater. Don't get confused. Both in case of power plant, regenerator and feed water heater are same. A feed water heater is basically a heat exchanger where heat is transferred from steam to the feed water either by mixing the two fluid streams, that is open feed water heaters, or without mixing them, closed feed water heaters. Now feed waters are of two types. So a feed water is basically a heat exchanger. As all of you know, the extracted steam or bled steam from the turbine is used to heat the water, or feed water is used to heat the feed water. So here the heat is transferred from the steam, that is bled steam, to the feed water by mixing the two fluid streams. So steam from the extracted steam from the turbine is directly mixed with the water coming out of the condenser, that is open feed water. So direct mixing, so it is called as open feed water, or sometimes the heat is transferred in the heat exchanger without mixing, so it is called as closed feed water heater. Now coming to the open feed water heaters, so you can see the schematic diagram, so as well as TS diagram. So an open or direct contact feed water heater is basically a mixing chamber where the steam extracted from the turbine mixes with the feed water exiting the pump. Okay, pump in the sense it is actually supplied from the condenser. Okay, pump is supplying this water from the condenser. So this is feed water. Okay, so you can see here. So from the boiler, so steam enters the turbine. So actually this point again is a mistake in the diagram. So you should draw it somewhere here. So it is extracted at some point here, not here. Okay, change this point. So this should, because at the same point you cannot extract the steam. So after bit of expansion, so steam is extracted. What is the quantity of steam extracted? So Y, right? So out of every 1 kg, Y kg is extracted. So the remaining steam, that is 1 minus Y kg, expands further in the turbine and it passes through the condenser. It condenses, right, to initial pressure or temperature 1. So then it is pumped. You see the pressure increases during the first pumping. Then here you can see the pressure is P2, and the bled steam which is coming from the turbine at this point. So those two, steam and this water from the pump 1 which is coming at state 2, mixes to reach the saturated liquid point or state at point 3. You see here the steam is bled. As I told you earlier, don't draw this line because these two lines should not be straight. Okay, this line and this line. So there somewhere here you have to mark the extraction line. So this you have to mark it as Y. Okay, here. Okay, that is 6 and it is entering in the open feed water heater. You can see here, you see 5 to 7 is expansion in the turbine, but after partial expansion at 0.6 little quantity of steam is extracted. So this quantity is Y. What is extracted here is Y. So remaining is 1 minus Y, means every 1 mass 1 kg steam flow rate. Y kg is extracted here. 1 minus Y kg passes through the undergoes further expansion and passes through the condenser. So this is open feed water heater where the steam extracted and the feed water at state 2 directly mixes and reaches the saturation point at 3, which is further pumped using second pump to the boiler pressure at 4. So ideally the mixture leaves the heater as a saturated liquid. So that is what the exit of the open feed water heater, point number 3, you can see it is on the saturated liquid line. So it is a saturated water, okay, as a saturated liquid. The schematic of the power plant with one open feed water heater, also called a single regenerative cycle, and the TS diagram are as shown in the figure. So this schematic of the steam power plant shows one open feed water heater, which is called as single stage regenerative cycle, and also you can see the TS diagram. The ideal regenerative Rankine cycle. In ideal regenerative Rankine cycle, the steam enters the turbine at boiler pressure or state 5. So as all of you can see, so this is the entry point to the turbine, that's 5, expands isentrophically to intermediate stage at 6. So I am just going through this explanation. Now steam extracted at this state is routed to the feed water heater, while the remaining steam continues to expand isentrophically to the condenser pressure 7. So partial of that is Y is extracted and at 0.6, so 5 to 6 complete expansion of the entire mass of the steam, but at 6 Y kg is extracted, so remaining 1 minus Y kg undergoes expansion from 6 to 7 in the turbine and it is passing through the condenser. So that steam leaves the condenser as saturated liquid at condenser pressure. So at the end of the condenser you can see it is a saturated liquid. Okay, so at state 1. So I am just going through the explanation. The condensed water, which is also called as the feed water, feed water, then enters the isentropic pump where it is compressed to feed water heater pressure. So here this is coming at certain pressure. Okay, again this diagram should be like this, not this line. Okay, so this is at certain pressure. So at the same pressure, so it has to be compressed or pumped in the pump 1, then only it can enter the feed water heater. Okay, open feed water heater, and you see that is what, where it is compressed to the feed water heater pressure and is routed to the feed water heater where it mixes with the steam extracted from the turbine. So here mixing takes place, the steam extracted as well as the feed water mixes. The fraction of the steam extracted is such that the mixture leaves heater as a saturated liquid. Now you have to, as an engineer, you have to think what should be the, or you have to calculate what should be the quantity of steam you have to extract. So you have to extract such a quantity of steam which after mixing with the feed water becomes saturated liquid at 0.3. So this is very, very important in the design. Okay, the second pump raises the pressure of the water to the boiler pressure, as I told you earlier. So this is what I explained earlier, same thing, but I am going through the slides. So here you can see the pressure 3 to 4 is the compression in the second pump where the pressure is increased from 3 to 4. The cycle is completed by heating the water in the boiler to the turbine inlet temperature and pressure in temperature of 5, because pressure P4 is equal to P5. So only temperature increases in the boiler heating. So now for every kg of steam leaving the boiler, so let us assume that Y kg expands partially in the turbine and is extracted at 6. So remaining 1 minus Y kg expands completely to the condenser pressure. So this is what I told earlier. If you take every 1 kg of steam, so let Y kg is being extracted, right, and is supplied to the feed water heater, and the remaining 1 minus y kg expands further in the turbine and enters the condenser. The heat and work interactions of the regenerative Rankine cycle with one feed water heater can be expressed per unit mass of the steam flowing through the boiler as follows. So now let us analyze this. Now Q in, so 4 to 5 is the boiler, so H5 minus H4. Q out, what is lost in the condenser, now it is 1 minus Y into H7 minus H1. So I can't go back to that TS diagram, just you recall, right? If I draw here 1 to 2, 2 to 3, 3 to 4, so then sorry, so here partial extraction at this point, okay, then expansion like this. Okay, I'm not drawing the dome, just I'm drawing here. So 1, 2, 3, 4, this is 5, this is 6, this is 7. Okay, so here H5, you see 4 to 5 is a boiler here, these two. So H5 minus H4, and here 1 minus Y kg is passing through the condenser from state 7 to state 1, this is the 1. So 1 minus Y into H7 minus H1, then W turbo output, so 2 expansion, 5 to 6 complete 1 kg expands, so here work is H5 minus H6, but remaining 6 to 7, the expansion is taking place only for steam of quantity 1 minus Y, because Y kg is extracted 0.6, so remaining 1 minus Y kg undergoes expansion from 6 to 7. So turbine work will have two terms, very important, and pump in, two pumps are there. First pump is handling 1 minus Y kg into W pump 1, and second pump is handling complete 1 kg of the mass, so it is plus W pump 2 in. So Y is the fraction of stream extracted, which can be calculated as m.6 divided by m.5. Okay, mass flow rate at 6 divided by mass flow rate at 5, and pump 1 is nothing but V1 into P2 minus P1, whereas pump 2 is nothing but V3 into P4 minus P3, because 3 to 4 this is the pump work second, 1 to 2 is the pump work 1. So this is V1 into P2 minus P1. Similarly, this is V3 into P4 minus P3, because V4 is the entry point to the second pump. So specific volume has to be always taken at the entry point. The thermal efficiency of the cycle is given by eta is equal to net work done divided by heat supplied, nothing but Q in minus Q out by Q in. So Q in is nothing but H5 minus H4, whereas Q out is nothing but 1 minus Y into H7 minus H1 divided by Q in is nothing but H5 minus H4. So this is the expression for the Rankine cycle with one feed water heater, that is open feed water heater. Okay, so with this I conclude this lecture number 4, and will continue with another type of feed water heater in the next lecture. Thank you.